problem or for the final?
Oh, this is for problem 57.
Oh.
We're gonna do problem 57, or you guys are gonna try it. And this will be the last thing. All right, so I have a mass of aluminum of 0.45 kilograms.
Oh, this is part of our homework.
And it is solid at 130. And it is liquid at 660. And the latent heat of fusion is 4 times 10 to the 5th joules per. And the question is, how much energy do you need to add to the system to take it from a solid at 130 to its melting point at 660? Let's see what you can do. Like to talk us through it?
No.
Here, I'll help you. Here's where we start.
Yeah.
And what kind of phase are we in right here? No, phase. Like
Salt.
Solid.
solid. So realize as we add energy to the system, right, we're adding Q, well, all we're doing initially is raising the temperature of the solid from 130 to 660, right? Then, at some point, the melting point, let's make sure we're clear on what's happening. This is all solid here. What do we have in this region?
Liquid.
It's a little bit of both, like a slurry, right? It's solid plus liquid, right? And then how about right here?
All liquid.
All liquid. Does that make sense to everyone? When we go through this flat spot, when we get to the end of it, we've completely torn the bonds of the solid apart. And it's all liquid right here. All liquid. And then if we continue to add energy, the liquid would rise in temperature also. Okay? So there's two pieces that we need to consider in the calculation. We need to consider this and this piece. So Q total is MC delta T. That's this piece plus MLF, latent heat of fusion, because we're going from solid to liquid. And if we went this way, we'd still use LF times M. That's how much heat would be given up. Energy would be given up if we started solidifying. Okay? The mass, 0.45. The heat capacity we need to look up of an aluminum solid, we need to find it from the table. Anybody?
900.
How much?
900.
9, oh yeah, we did that, didn't we? What's the final temperature?
660.
660 minus 130, where we started, plus the same mass times this constant. Yes? 4 times 10 to the 5th. Are there any questions about that? This is accounting for both processes as I add heat to the system. You could even think of it maybe as a, stick of butter or something. Put a stick of butter in a pan, it's solid at first. As I add more energy to the system, its temperature increases, and then at some point you get, remember, like a runny solid combination, and then at some point it completely melts. I mean, this kind of shape is consistent for most things that go from solid to liquid to gas. I just used water in the example, but the ideas still work. All right, that's it. Oh, what was the answer? Q in the system was 3.9 times 10 to the what? Fifth joule. That's how much energy I need to put into the system.